Welcome back, my steel design friends. In our last video, we talked about a concept known as shear lag, in which it was the distribution of an axial force over a cross-section, and we talked about these net areas that were actually effective in carrying the load. Okay. In this video, I'm going to show you how to quantify that area using the shear lag coefficients of the AISC manual. So without further ado, let's get started. The shear lag factors, or the shear lag coefficients, are found in a table located in Chapter D of the specification. I'm looking in the 15th edition at 16.1-30, and in particular, this table D3.1 is kind of the key to all of what we have happening here. Now, there's a lot of words that are happening in here, and so you've got to read very, very carefully the different cases. There are a total of 8 cases on here, and so we're going to kind of go through these one by one just to kind of illustrate some of the more important keywords that we're looking at. All right, so if we look at case 1, this is all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds, except as in cases 4, 5, and 6. So then, unfortunately, there's a lot of this. Well, this was the case, but you got to make sure that it's not these others. Okay, so 4, 5, and 6 have to do with plates, that are welded, welded on the heels or on the ends, as well as some HSS kind of sections. Okay, so this would be kind of your flat plate scenario. In the case of, we're thinking about shear lag and the flow of those forces that we talked about in the last video on this. If our section is has enough bolts in it that it's reasonable to say that the entire cross section is being loaded, and that's typically in a case that might be something like, a flat plate on here. So if I come in and just real quickly sketch this guy, that it's just a flat plate, and we play our flow net game, and I put a couple bolts, 2 bolts across this section, and I load this, and this connection is long enough. Well, it's possible that my effective area, as I start to trace that boundary line like we did in the last video, that if this is my net fracture, my net fracture plane at this location, well, then it's safe to probably say that, yeah, that's pretty much fully effective. This is a U of 1.0. Okay, there is no reduction of the net area when I calculate my effective area. In fact, this was the case that we did in our example 2 videos back when we started talking about the net fracture definition in general. Okay, so you can kind of see that, my area is pretty much the entire thing is being loaded, by the way that the loads are being applied. Now, again, this assumes that the load is over the entire cross section. If you had which means that my point load is acting here at the centroid. If my point load were acting up here or something, well, then you start getting into some dead areas or something. If it was a load that's being applied by, say, a bolt that's off here, and then we're pulling on something like that, you've got to be kind of careful on that definition. That's why it's important to be able to understand how these forces are flowing through things as we start to look at. But that's case 1, is when it's safe to think that every element in the cross section is being used to help with the load. Okay, case 2 is kind of your general catch-all. Okay, and this is all tension members except HSS, where the tension load is transmitted to some but not all. Okay, so notice the difference. Before it was transmitted to all, directly to each, and now it's some but not all, meaning that, if it's an I-beam, I'm bolting the flanges but not the web, or I'm bolting the web but not the flanges, or I'm doing an angle where I'm only bolting one leg. All the rules for that. Okay, so it says to some but not all of the cross-sectional elements or fasteners, or by longitudinal welds in combination with transverse welds. Okay, now we haven't talked about welds, but what a weld is the case that they're talking about is if I take that same plate and instead of bolting it, with a PU here, let's just say that I weld this side. This is called a longitudinal weld. Okay, And if we imagine our flow net diagram on this, this is very similar to what we were seeing with the I-beam, that some of the load, if we kind of start to that maybe it goes to that back corner, that this becomes my effective area on there. But we do have a big dead zone in here that's not. So if I were to think that this is my net fracture plane on here, well, then I'm looking at an area that's here, and I'm looking at an area that's there as being the loaded area. So this would not be a U of 1.0 case. Okay, but if we come in and were to put in a transverse weld on the back end of this thing, this is a transverse weld. And again, their orientation is based off of the orientation of the load. So a transverse weld goes across the load or perpendicular to the load. A longitudinal weld is running parallel to it. Now this arrow, it's going to here, but it's also going over to here, and it's coming over to here. And now what you've done is you've started to load the entire cross section much more effectively as you start to kind of look. So you can see that the dead zone, now we've recaptured the capacity and put that guy to work for us just by putting in a simple weld on the back side. So that's what it's saying. Now the formula that we use for this case too, for this is because these welds are at different lengths, it's not fully effective, but it is better. So that's why if you've got a transverse weld in conjunction with longitudinal, I'm going to use the second case, this case 2, which is 1 minus x bar over L. Okay, and so the question becomes, well, what is x bar? Okay, and so they've got these little diagrams over here, and they're not real clear in here, but you can see that, for an I-beam in the Y direction, if they're welding to the plate, the X bar is taken from the center of the member out to the extreme edge of the plate. That's the X bar. If you're putting a plate on top or bottom flange, now it goes from the top of the plate down some amount X bar. Okay, well, the question is, well, what is X bar? So what we want to look at is we want to go in and we want to go back and look at, again, the commentary for the effective net area. And they do a real good job of explaining how they calculate these X bar values, especially for things like I-beams and stuff. So if we flip over to the second page, I am up on page 16.1-300 on this. This gives you the rules for how they calculate the X bar value. Okay, what it is that it's a distance that reflects, in this case for an I-beam with bolts in the flanges only, they're calling it as an X1 dimension. Okay, and so what they say is you take an I-beam and you cut it in half. So that kind of goes with our assumption that the upper part takes the upper load and the lower part takes the lower load. Again, right or wrong, that's the way it's treated. Okay, and you treat it as an equivalent WT section. Okay, and so the way that you calculate X1 bar then is actually spelled out for you over here in the paragraph here. Okay, and so you've got to kind of read through a lot of this. Okay, and so this is exactly what it's saying. It says the member is treated as two WT shapes because the section shown is symmetric about the horizontal axis, and that axis is also the plastic neutral axis. The first moment of area above the plastic neutral axis is Zx over 2, where Z is the plastic section modulus of the entire section, and the area above the plastic neutral axis is A over 2. So by definition, this X1 bar dimension is now Zx divided by A. So when we're calculating calculating mu, this X1 bar dimension is now D over 2 minus Zx over A. Okay, and so what it is it's basically, it's figuring out the centroid of this thing, and it's assuming that at the centroid here is where the load is acting. Okay, so the function of this X bar parameter is the distance the load has to move from its resultant location to the effective connection location on there. And so they're taking a D over 2 minus, it's basically that distance as it was spelled out is basically the distance from here to here on this particular shape. Okay, for other shapes, it's very similar to being done. So now I've got a channel with web holes in it, and so the X bar then is taken from the back surface of the connection. So this is what we call the faying surface. The plate would be bolted here on the side of the web of this thing, and we take it to its X bar value as calculated over here. Okay, so for the I-shaped members with bolts in the web, as shown in figure D3.1c. The shape is treated as two channels and the shear plane is assumed to be at the web center line. Okay, using the definitions just discussed, but related now to the y-axis yields x bar is equal to zy over a. Okay, so those are kind of how we start to kind of come up with these different values for this particular calculation. It's a little bit cumbersome, but it's a better representation of how much, it's almost like eccentricity, or how much does that axial load have to travel across the cross-section to get to its connection surfaces. And that's exactly what it is that we're looking at, okay? So this is how a single channel was done, and so then for an I-beam, we're basically going to deal with half of it. So it goes from the center line of the section out to what they're calling is X bar, and that's what we're doing it. Now, the other dimension that we have then is the L dimension. Remember, if we come back to here, we're looking at 1 minus X bar over L. Well, what is L? Okay, well, L is considered to be the length of the connection. Okay, and this commentary shows you what that is. In fact, this diagram tells you everything. That if I have a pattern of holes, L is taken as the out-to-out dimension of the holes. Okay, so I would go not to the center of the hole, but to the outer edge of this one, and then to the distance of the center of the hole to the outer edge of that one. Okay, and that's how we start to come up with our L. Okay, and then the X bar then is from the fang surface up to whatever the X bar value is being calculated as. Okay. Now, the good news is that these X bar values are tabulated for you up in the sections. At least for angles, they're tabulated up in the section property sections that we talked about. Okay, but the L is an out-to-out dimension according to this. Now, in practice, I typically just take it as a center-to-center value, right? Something that's just a little bit smaller than what is allowed. Okay, just for the ease of calculation, and it'll cost me a few percent. But it saves me time in the calculations. And generally speaking, when I've done the details, I have the center to center of the hole dimensions, you know, and so it just gives me a little bit of extra insurance. It doesn't make a huge difference on that. But AISC says it can be an out-to-out dimension on this, okay? And so that's kind of the nature of where those parameters are coming from as we start to look. So again, back in D3.1, and you'll notice in this one, I have a yellow tab on this page because that one I use a lot. So this is probably a good one to bookmark if you're one of my students, because we're going to be coming back and forth to this quite a bit. Okay. All right. So now we can go in and we can look at case 3. Okay. And that is the case where all tension members where the tension load is transmitted only by transverse welds to some but not all of the cross-sectional elements. So did you catch the keywords here? It is now some but not all. Okay. And so the tension load is transferred by only transverse welds. So, well, what's the picture that they're talking about here? Well, this is the case. You remember, if it was a full transverse weld, on there, get my straight edge here. If it was a full transverse weld, like what we defined up here, we were able to get a very high U value. In fact, U could be 1.0 in some cases. The case they're talking about here now is, say I have a plate, you know, such as what might be on a stiffener or a gusset or something, that's being loaded here. Okay, but now I only weld a portion of it. Okay, well, think about what's happening with the load. When it was the full length, the loads pretty much went straight across, but now it's starting to do something like this. Okay, so here's my effective area, and so my net area for this calculation would be here. Okay, and so we've got to do something to calculate what is that area, and that's what this provision in case 3 is trying to do. Okay, so what they do is they say, well, all right, U is still 1.0, okay, but now AN is the area that is directly connected to the elements. So if you know, say the width of this weld, if we call that as some W, and this was a plate that's being connected that has some thickness there, okay, well then the net area on this is going to be equal to W times T. Okay, because basically we're looking at not the weld failing, but are we able, we're still in the base metal itself, that, what would it take to rip this little corner off? So the smaller that weld is, the smaller AN is, and the smaller AN is, the smaller AE is, and the smaller the net fracture calculation is. So that's why, when we're looking at these welds, we like to have a little bit more length on them because it spreads the load out a little bit better, and I don't get that stress concentration down in the corner. So that's our case 3. Okay, and then the rest of these you can kind of read through. We don't use them a whole lot, but we do. Case 4 is for plates, angles, channels with welds at heels, T's, and W shapes with connected elements where the tension load is transmitted by longitudinal welds only. So they've changed the wording of this one a little bit since previous editions, but again, the diagram is basically, it's a longitudinal weld only. So we talked about that one, and then so based on the dimensions, you have L1 and L2. Okay, the L is going to be the smaller of the two, and then the W is how far apart are those welds as we start to look, okay? And then, of course, the X bar dimension is the same as what we were talking about. So that's how you would calculate your U value. The next couple of cases are all for the HSS cases. Maybe I have a plate that's going down the middle of a tube steel round or something. That's this one, or a square round, okay, with a single concentric gusset plate, okay, and then or 2 gusset plates, which would be the gusset plates are on the outside. So you can, these are pretty self-explanatory on what those are, and they give you the dimensions to use. D is the diameter of the pipe, H is the length of the side that's parallel to the plate, so forth and so on. And so you can kind of see how you would calculate your U factors pretty straight away. Okay, the other ones, the last 2 then pertain to the rest of the ruled shapes. Okay, so case 7 and case 8. And if we look, case 7 is W, M, S, or HP shapes, or T's cut from these shapes. Okay, now, you'll notice at the very end of this, though, is an extra statement that says, if U is calculated per case 2, then you are allowed to use the larger of the 2 values on this, okay? So the cases that are down here in 7 is with flanges connected with 3 or more fasteners per line, okay, meaning I have 3 bolts in a line, not in a cross section, but in a line down the length of the member. I can calculate U based off of the comparison of the flange width to 2/3 of the depth. And you can see that for flanges being connected, I can go from 0.9 down to 0.85. Now these are really easy to use, okay, but they may be a little bit conservative depending on, again, if we go back and look at case 2, if the length goes up, then this second quantity goes down. I can actually get close to 1 if I have a really long connection that's in the flanges. So, but these are good first estimate guesses. And then if I want to sharpen my pencil a little bit, sometimes I can get a savings in 2. You don't have to do that, but recognize that if you don't, you may be giving material away and coming up with an inefficient U value on that. Okay, and then if it's with web connected with 4 or more fasteners per line in the direction of loading, then I can take U as 0.7 just straight away. Okay, because the flanges aren't doing any work for me. Okay, now if you have bolts in both the flanges and the web, now I'm back up to case 2. So you have to be very explicit that you meet all of the criteria and nothing more for what's happening in case 7. All right, and then case 8 has to do with single and double angles. We kind of explained this case in the last video, but it too has the same note that if you use case 2 to calculate this, you're permitted to take the larger of the 2. And you can see, in this case, with 4 or more fasteners per line in the direction of loading, okay, U is 0.8. Okay, with 3 fasteners per line in the direction of loading, with fewer than 3 fasteners per line in the direction of loading using case 2, then U is a 0.6. And again, that's kind of a reflection on growing that L length on there. So these are, if you're just doing a preliminary sizing of a member, you don't know what the member size is and you haven't detailed it, these are good starting points because you'll never be worse than these values according to what AISC allows you to do. But once you've got your configuration laid out, your connection determines bolt spacings and the gauge distances and all that determined, you're better off coming back up to 2 and checking that value that we had up here. So this is kind of the catch-all version. If none of the other cases apply, you're in case 2 for computing these particular values. All right, so that's kind of how table D3.1 works. You got to be very careful in what you're reading and make sure that you're catching all of the key words, some but not all, or directly to each, of the elements. Those are all the key words that you're looking for in this table. All right, so let's kind of go through just to wrap up again real quick the cases that we talked about. Okay, and that's kind of what we were seeing here, that for a transverse weld case, this would be a U of 1.0. For a longitudinal weld case, these were the criteria that we had to deal with. And again, we've kind of explained all of this. I want to kind of look at, for example, I kind of get into one of the WTs. A W14 by 82 on this is going to be taken then as the distance from has the section properties of TF of 0.855. It has a web thickness of 0.510, and the height is 14.3. These all come out of the member specifications on this. So according to this, what we need to figure out is, well, what is my L in this? And so my L in this is 3 inches plus 3 inches, okay, which would be a length of 6 inches. Would be, if I'm looking to calculate, what my U value is from 1 minus X bar over L. This is also the 3 bolts in a flange case, which would be down in, if I pull this back up here, okay, with the flange connected with 3 or more fasteners per line in the direction of loading. So I could come in and I could do this calculation, that BF is greater than 2 over 3 times D, and say if it's less than that 2/3 of D value, which U are we using? So for case 7, this particular one would be, since I know BF is 10.1 and D is 14.3, that's a 0.71, okay, and that is greater than 2/3 of my depth. So you can see that what I did is I divided D out of both sides of this. So now I'm just comparing this number to 0.67 to 2/3. Okay, and so 0.71 is greater than 0.67, so clearly we're in the U equals 0.9 case. All right, so this is our case 7 happening here. If we try to apply this to case 2 on here, okay, well, we have to do something a little bit different. Let's do U equals 1 minus X bar over L. Okay, the length of the connection we said was the out to out of the holes. Now we don't specify the size of the bolts or the size of the holes at this point. I just know that my spacing is 3 inches. Okay, and this is a fairly typical arrangement of bolt spacings, and I-beams is a 3-inch length down that way. So my L in this case is going to be something slightly greater than 6 inches. I'm just going to use 6 inches for my L. So my challenge then is I have to go figure out what is the X bar happening on this thing. All right, and so the way that we do that is we go in and say, well, our shape was a 14 by 82, but if you remember the commentary, it says we're now looking for a WT equivalent that is half of that. So this is going to be looking at the 7 by 41 table here for the WT. So I'm going to pause the video and go find that guy real quick, and I will be right back. All right, I'm back. Sorry about that. Okay, so reading through the commentary, I realized that I misspoke, that it's not the WT, so we don't need that guy. Instead, we're going to use the section properties. The way that it was written is they converted everything back to the original W section by their equation. And again, according to that paragraph, this X bar, this is the X bar 1 value that we're using, is D over 2 minus ZX over A for my shape. All right. So if we go through, we've got D we said was 14.3 inches. Okay, and if I look on page 1-24 of the manual, I can get the section properties for this 14 by 81, that ZX is 139 inches cubed, and AG is 24 inches squared. And if I plug those values into this equation, that's what I'm doing here, 14.3 divided by 2 minus 139 divided by 24 gets me an X bar value of 1.35. This is real close to the K value for this beam. It's a different value, but if you want to use that as a first guess, that might not be too bad of an assumption, but we're going to be pure to the calculations, and so 1.35 is what we're going to use. And then going into case 2, it's 1 minus X bar over L. That's this formula. I now have my L of 6 inches. I have my X bar of 1.35, and if I calculate U from this, I get a value of 0.78 from case 2. Now again, the note on the bottom of case 7 says you're allowed to use the higher of the two. So this is what you're going to use as your controlling U value. Okay. Okay. So most of the time you get a better estimate on this, but because this connection is so short, we got kind of penalized. It's only 3 bolts in a row, and they're pretty close together. If I had changed this to, say 5 inches on center spacings, so that it was a 10-inch L value on this, then I would do 1.35 divided by 10, and then subtract 1. We would be looking at a 0.87 on that. So it's, it's, take it for what you will. It's getting closer to this value. So this is a pretty good first guess, and they're comfortable with letting you use that as you start to kind of look on the code on that one. Okay. All right. So that's all we have for shear lag. And at this point, once you have the U value, now I can take that and plug that into my net fracture equation. So what will happen is if we want to kind of finish this calculation out, I'll do it by hand since I don't have it pre-worked for us, is that if we were looking at this particular example in which I'm bolting the flanges, okay, they'll look something kind of like that. Let's just say, for the sake of argument, that these are 7/8 inch diameter bolts, okay? And so then we know that my gross area on this is 24 inches cubed. And so then my net area on this is going to be A gross minus 4 times the area of the holes, because there are 4 holes in my cross section, okay? And then my area of my hole is going to be equal to then the diameter of 7/8 of an inch plus the 1/8 for punching and oversize, multiplied then by my TF value gets me that. And so now I can do 24 inches cubed minus 4 times, well, that's 1 inch times TF, so it's a 1 inch times TF gets me that value. And so whatever TF ends up being, I forgot to look that one up. Let me pause it again, sorry, let me grab that one. All right, so looking it up in either the WT table or the W table, the TF on this is 0.855 inches. Okay, and so this guy is 0.855 inches, and if I calculate that real quick, what do we have? We have 4 times 0.855, and then I'm going to take that from 24. Our total gross area is going to be, for our net area, is 20.58 inches squared. Okay, and then that means that I can calculate the effective area then as being U times AN on this. And so that will get me, my U we said was 0.9 from case 2 and case 7. So I'm kind of writing sideways here. Case 7 multiplied by then 20.58 inches squared gets me that. And so if I multiply that number by 0.9, that's 18.52. Gets me that value. And then if I want to calculate the net fracture capacity, we know that that's going to be PN is going to be FU times AE. Let's just say, for the sake of argument, this is A992. So that's going to then be 65 KSI. Okay, multiplied then by 18.52 inches squared, that this member would have a rating of 1,204 kips. It's a pretty big load. It's a big member to be putting into tension. 1,284 kips, about 1.2 million pounds, if you will. Now, that's the nominal strength. If I want the design strength, then I take phi, which is 0.75, and I multiply it by 1,284 kips, and that gets me to my final answer of 903 kips in tension. Still a large number. All right, and that's how you do a net fracture calculation with the shear lag factored in. All right, so we lost about, if you look, we lost about 10% of our strength just because I didn't bolt the web of this thing. And so depending on your, how the case that you're in for calculating your U value, this is the way that we do it. So I hope that's made sense to you. I apologize for the little mix up there and the unnecessary pause in the middle, but hopefully this has been pretty clear on what it is that we're trying to do as far as values go. So this is a very common set of calculations that we have to do. You've got to calculate your net area, you've got to calculate your shear lag coefficient to get to your effective area, and then that's what goes into the net fracture calculation. Now, what you do once you have net fracture is you compare that to the GY case on here. So maybe I'll go ahead and do that one real quick. So Fy times AG, that this would be 50 KSI, and my AG we said was 24 inches cubed. So if we do that, 24 times 50 is 1,200 kips, and then phi PN of this guy, the phi for gross yielding is 0.9, and I multiply that by my 1,200 kips. Okay, and if I do that, 0.9 times that value, I get 1,080 kips. And so the smaller will be the one that controls. So the capacity of this guy in tension is only 903 kips, even though gross yielding is significantly higher. Now, what this tells you when we look at net fracture and gross yielding is that, that net fracture is being governed by the details of the connection, the size of the bolts, the length of the connection, what have you on this. Is that there's some issues with the detailing on this, that I could get more capacity up to about this value. This is like the theoretical maximum, if you will, that I could count on. But by changing my details, I could drive this number up. Like maybe you make, instead of 3 bolts in a line, you make it 5 bolts in a line. Well, you just drove L up, or you change the spacing. I can tweak this. I can tweak the net fracture number. The gross yielding I'm pretty much stuck with. Okay, and so that's why you're looking for anything lower than gross yielding, and that's why this one controlled at 903. So anyway, I hope that made sense to you. Again, as always, if you've got any questions, leave us some comments down below. Otherwise, be sure to like and subscribe to the video, and we will see you in the next one. Happy engineering.